Integration strategies, some approaches that we can take when solving integration problems. The first one, as the name suggests, is obvious. Look for an obvious solution. What do I mean by that? Well, try to find some function in there. You've got an integrand, but the derivative is also there. You're looking for something like that. So I see this sort of question, and I go, okay, well, the derivative of x squared is 2x, so I can manipulate this to get it into that familiar form of derivative times a function. And then when I've got it like that, and by the way, here's that non-standard integral that's worth remembering, it's du on root u basically. So we go 2 root u becomes minus root 1 minus x squared, plus of course a constant. Well, that then brings us to the second idea. We want to manipulate it into a standard form that is on the reference sheet. So the standard integrals, they're designed to save you time. Like when I was at uni, the calculus textbook that I had, which was about that thick, but in the back of it, it had something like 500 standard integrals. So just for all different situations. It's just to save you time. You're doing a problem, you'd look up the standard integral. Oh, okay, that's the solution to that one. Bang, let's move on with the problem. So that's the idea behind these lists of standard integrals. Now, obviously, you don't have 500 of them to look at, but you've got a handful there that you can use for the exam. But once you've manipulated it into that form, then great. You can work out the primitive function. You just quote the answer. Here you go. Look at this. The integral of e to the x plus e to the x. So the power is x plus e to the x. Again, not immediately obvious here how we can manipulate this, but that's how we manipulate it. If I use my index laws, I can rewrite that as e to the power of x times e to the power of e to the power of x. It's now in the form derivative times function, because the derivative of e to the x is e to the x. So therefore, the answer is just e to the power of e to the x plus, of course, our constant. Let's have a look at that. It's inverse tan. So the form I'm looking for is derivative on a squared plus function squared. Because I note on the bottom I've got e to the power of x. On the top I've got e to the power of half x. Well, e to the power of x on 2 squared is e to the power of x. So to highlight that, I've just rewritten it and manipulated it to get what I want. Because if the function is e to the power of x on 2, then ideally the derivative that I'd like on top is a half e to the x on 2. Playing around with the numbers, that means the denominator becomes 2 plus. That's in the form of inverse tan. Oh, sorry, and I should have said, it also means I have to pull out 4/3 as a constant. That's in the form of inverse tan. Don't forget the one on a as well, so I've also got the one on root 2 in the answer. How do I write it? Yeah, the root 2 goes into the 4, so I wrote it as 2 root 2 on 3 inverse tan of that beautiful expression. You see, extension 2 integrals, way more fun, way more fun. Simplify the integrand, if possible. Algebraic manipulation, trig identities, these sorts of things we can use. So let's do a trig one. Here's tan theta on sec squared theta. And you look at it and you think, oh, brilliant, I've got the derivative in the function. But unfortunately, with our standard forms, I'd like the derivative on the top and the function on the bottom, and I've got the reverse of that there. So I'm going to manipulate my trig. Let's turn everything into sines and coses, and let's see what we got. Tan is sine on cos. Sec squared is the reciprocal of cos squared. Well, I've now got some cancelling. I end up with simply sine theta cos theta. I could have gone from that step because, of course, we have derivative time function, but I recombined it into one thing and said, well, that's a half of sine 2 theta. Either way, I'm going to get an answer. Integrate the sine 2 theta, and of course we get minus cos for that one. X cubed times the square root of 4 minus x squared. So the idea for this one, I'm going to factorise this. Factorise it? What's there to be factorised? But what I do is I have a look for the expression in the grouping symbols, which in this case is what's under the square root sign. So 4 minus x squared, I want to create a multiple out the front, or of that function itself, or its derivative, or maybe a combination of both. That's what I turn it into. Now, if you follow through those brackets, that is x cubed. But you see what I now have? I have that function, or its derivative, or a combination. Okay, so I've got x times 4 minus x squared. 4 minus x squared was the function, but I knew I needed to get x cubed, so I multiplied by x, which is a multiple of its derivative. But to balance it out, I need to add a 4x, and that's okay, because again, that's a multiple of its derivative. Why on earth do that? Because now I can rewrite it like that. Each of those expressions is derivative times the function. So it's just add 1 to the power over the power. Okay, I've got to play with some of the numbers to get these derivatives right. I need 2x in these, but there you go. Add 1 to the power over the power in each of those, and we have successfully integrated it. Let's tidy up those numbers and make it look impressive by putting them back in the third form. But there's the answer. Classify the integrand according to its form. So you look at the form of the integral and it tells you the technique that you're going to use. Now some of these techniques we haven't seen yet, and we will see them. But for instance, if you see rational functions, so those polynomials over polynomials, those sorts of things, then do the polynomial division. We've seen that idea already, but some of the more complicated ones that we'll see will end up using what's called partial fractions to go and solve that. Trig functions. We've touched on trig integrals so far. We're going to look at a lot more. But the power of the trig function will tell you the technique that you use for that function. And if there's a mixture of different functions, then it's probably this thing we call integration by parts. Again, something we're still to look at. Essentially, every integral, there's just 2 methods: substitution or integration by parts. That's essentially it. It's going to be one of those 2 things. Okay, we might have to do some manipulation to get it there and what have you, but essentially that's what we got. So just our little opener there, looking at different techniques for integration, so 4a and 4b.